So, hello everyone, thank you for joining the Journal Club today. And today I want to to tell you about a pet project I was doing this spring. And I always wanted to do something about natural language processing. And I did some pet projects in the past as well, but this is the first time when I actually got some results. Because of two reasons probably. First, because it was a small project. It was a very small project, and we just picked one grammar error in Russian language which we wanted to correct. So instead of doing something big, something huge and very complicated, it was just one error, so it was easy to get the result. The second reason was that I wasn't doing it alone. I was doing it with a student of Ural Federal University, so my alma mater, and we were splitting the work in the following way. So Ilya was mostly doing actual research, so featureization, model building, run of the models, evaluating the research, and I was mostly supervising it and also tried to understand how we can scale it. How can we then use the same methodology, the same approach for all other errors in Russian language which you probably know are abundant. So, so that was also a very important factor contributing to success, because working with someone is always nicer. And what was the issue? What was the error we were trying to correct? So basically the problem was very alike to the English language in these two sentences. So the first sentence is he likes it, and this is a finite form of the verb like, and it has an ending s. But if you change this sentence into he should like it, then like is already an infinite form of the verb, and as such it doesn't have s in the end of it. And in English language it's easy for a non-native speaker to do this mistake. I hear it quite a while from everyone. In Russian language it's a little bit worse, and that's why. So this is roughly the same sentence in Russian language, and here is also roughly the same sentence in Russian language. And you can notice that the verb, so this is the verb, they are different in just one letter. Unfortunately, this letter is not to pronounce. So both sentences, the word to like, понравится, in both sentences is pronounced in exactly the same way. So you just don't think about such things when you write, right? So the only moment when you need to think if it's a finite or infinite form is when you actually write. But also it doesn't happen with all the verbs. Most of the verbs have different vocalization in finite and infinite forms. So this is a small class of verbs and small class of situations. You have to make this distinction, and you just don't. And this is probably the most widespread grammar error in Russian language, at least in those that are easy to correct. So there is of course lots of punctuation issues, but usually you just don't care about those. So you just write somehow and that's fine. But this one is really widespread, and it's also really irritating for some readers. So what is the state of the art for the ways to control this and other grammar errors in Russian language? So we have Microsoft Word, which can catch it, but other than that we don't have much. So for English language we have Grammarly. For German language I have heard of two startups that are trying to mimic Grammarly. And our ex-colleague is working in one of them. So, but for Russian language, I haven't heard about it, and there is no solutions available in the internet, at least for free. And for a paid version, I guess they just reroute the requests to Microsoft Word. So we decided to try. Why not? So this is one error. Basically you have to determine if the word should be in finite or infinite form. Yeah, let's do it. And we did. So how can we start with something like that? So 5 years ago, or maybe 7 to 5 years ago, we didn't have a lot of choices. You have to start what I call ab ovo, so from the very beginning. Maybe bag of word, maybe you need to use word to vec, something like this, but there's not really much solutions available. And the results are also not great. Over the last 5 years, we have seen an explosion in transfer learning for natural language processing. So the first model was probably BERT from Google, and the most recent one is GPT-3. And the approach that is currently taking off is let's just feed everything to GPT-3 and let's see what happens. And unlike, I think, everyone in the world, we Russians actually can do it, because for Russian language there is a free GPT-3 model available. So for English language you still don't have it. You have to apply to Microsoft, write a long letter about how you are going to use it in an ethical way and blah, 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 blah. For Russian language we do have it because our Sparkasse decided to train it for some reasons. We don't know why. But they did it and they made it available online. And that's great, so we can use it. But even though we can use this, it doesn't necessarily mean we want to. Because first, when you try to work with such models, I tried, it's extremely expensive to train. So you have to use a lot of computational resources. If you work on your laptop, it's probably going to take a while. If you work in the cloud, it's going to get faster, but also expensive. And also, the question we always need to ask ourselves is, do we really need it? Like, GPT-3 is a model that can understand the text to the extent that it can actually reply to it. So, if you just try to understand if it's finite or infinite form, it probably is too much, right? So our choice was use the existing solutions and deep learning as well, but only to generate features. And then in the end, so we don't train these deep learning solutions. We just use them in the way they are. And in the end, we just train a simple classifier that will tell us if the mistake was made or not. Now, how do we do this? So this is a description of our pipeline. And this is just an illustration. So how do we do this? We take all the sentences with the word in question. As I said, not all verbs have this problem of being very, very similar in finite and infinite forms. So we filter out for those. Then we generate the negative samples. So basically every correct usage of the word we replace with an incorrect one. Right? So for this approach, we only need a source of clean texts, and everything will work. So we use the newspapers. We could also use any other source. So there are enough of clean sources on this extent. So we couldn't do it with punctuation probably, but with this error it's totally fine. Then we featureize. And the features we use are morphology and syntax. And here I used the image from Google Cloud NLP solutions, which performs the very same task. So for each word in our sentence, we can obtain a number of morphological and syntax features. So morphological are here on the bottom. So this is the part of speech. And this is the morphology categories of this speech. So this verb is in indicative mood as opposed to imperative, for instance, singular number, third person, and past tense. right? And the syntax features are here. So first is what is the parent of this word in the syntax tree, right? So by tradition, the root of syntax tree is a verb. And for instance, the subject is a child of the verb, while the article here is the child of the subject. Also, you can have more deeper, it can go as deep as you want actually. So you collect these features, and I'm going to show you how, and this is going to be a main part of the talk. How can we manage all these features? And then you look at these features in the context of the word is in question. So the simplest context is the left words to the left of the word in question. So if the word in question is Berlin, we can take the context of these three words, the weather in, look at their features. Just feed all these features to the classifier. We used cat boost here because it works very well with categorical features, and this is essentially the decision trees, decision forest, and we were able to obtain 91% ROC-OC. How good is it? Oh, we don't know. So the best way is, of course, to compare it with MS Word, and that would give us a good understanding if it's a good result or not. But in order to do this, you can't do it manually, right? And what Microsoft Word does, it highlights the errors in your text. So you have to somehow read this output from MS Word, and we just didn't have time to do this. Okay, so that's the pipeline and results. And now I would like to talk about how we actually took control on this research, on these features, and on all this process with training grounds, and why it was a good idea to do. Okay, so first, what did we use as features? So this is language specific, and we used PyMorphy 2, which is a classical morphological analyzer. It just has a huge dictionary which shows for every word in which form it's used and what is a vocabulary form. And for syntax, it's much more complicated. So, I mean, building a syntax tree is hard. And I think the best, like the first working approaches emerged just recently. I mean, if we think about this, like a huge branch of computer science of 60s, 70s, 90s were also trying to do this, and this is how all the programming languages emerge. And when the compiler converts your program to assembler or whatever, it actually builds the syntax tree and converts the syntax tree into a machine code. But for a natural language, it was quite unsuccessful for decades until, again, Google released BERT-based solution for that. And this is a good solution. It's also available for lots of languages. Russian included, English as well, German as well. And what you see, so on this slide, this tree is again available from Google Cloud, and it's obtained by this model. But this model also has disadvantages. First, it's not designed for you just to run it for many, many different reasons. So last time I checked it, it was still Python 2. Yeah, so the problem starts there. Some enthusiasts have created a Docker container that somehow hides this problem as well as many others and allows you to run it communicating with API, which is also not the fastest way to do this. Also, it's huge because it's based on BERT, and so generally it's not something you want to have around, because if you want to use this in the future to actually test the texts, you also have to have this container somewhere around, and you don't want to do this. So, but again, we are lucky in Russia because we have a local solution for that. And this is Slovnet of the quite prominent team. So they do a lot of NLP tasks for Russian language, entity recognition on a very high level, apparently also syntax parsing. And what they did, they basically trained more or less the same deep learning network, but specifically for the grammar, for grammatic purposes. So it doesn't understand the language, but it understands it enough to solve the grammatical questions. And this is much, like 50 times less. So it has 50 times less parameters. Consequently, it works much faster, but the accuracy is the same. So we are just lucky we have it. So how do we process this information? So it starts on when we build what we call the bundle for our research. So we pick all the sentences we are interested in, and we create the negative samples out of them by replacing the correct form of the verb by incorrect form. And we store these sentences in index frame. So this is the main frame that we use in our research. And then we enrich this frame with the morphology or syntax or any other features and place them in different frames. So we don't want to join them all together because it's going to be too much of the columns. It's also not going to be manageable. And we just place them in separate data frames and supply them together basically in a zip file where all these files present. And then there is a known procedure of how we can extract the features. And this is an extraction step in training grounds. So we have the index frame, and some rows from this frame are selected for this particular batch we are going to process right now. And then we just describe from which table, by which index, which features should be selected, and we unite these features in a frame of this structure. So these features after extraction, they are already in numeric format. So if we had a category, if we had categories, the categories are already translated to one-hot encoding if it's required, and for neural network it's required. If we had the continuous features, then these features are normalized, so they are already can be fed directly to the network or other algorithm. So, and also we can combine features from different sources and create this basically, this is a data frame, but essentially this is a tensor we can feed to the network directly. But now the question arises, how do we do this for context? Because it won't help you at all if you just provide the morphological and syntax information about the particular word you are analyzing. Because this particular word you can find in, like, it can be correct, it can be incorrect by itself, everything is fine with this word. It's not the word, it's the context it's used in, right? So you have to compare this form, the morphology, the syntax of this word with the morphology and syntax of its environment. For instance, if there is a modal verb somewhere nearby, then probably it's an infinitive, right? Because this is a classic case when infinitive is used after the modal verb. I should like it. So the should is modal verb, or yeah, in this context is a modal verb. So on the other hand, if you look around and you see the noun in nominative case, then probably it's a finite form. So something like that. So, but if you look around this word and you analyze the structure of the words nearby, you probably are going to be able to answer this question. Another thing is that this is on the level of intuition. We have noticed that this syntax analyzer doesn't really work well on the sentences with errors, which is understandable because it's trained to build a syntax structure of correct Russian sentences, and if it's provided with incorrect Russian sentences, then strange things start to happen. And so if we just look at the syntax structure of the sentence, we might notice that this is weird. This is weird. Sometimes there are two roots, for instance, even. So just looking at this, we can maybe guess that something is wrong with this sentence and maybe this is this word. Yeah. So how do we work with this context? So initial solution was just hard-coded. So look at n words to the left and just stack the frames one after another. And that was fine right until we started to think, okay, but how do we look, for instance, now to the words to the right? Or how do we look at other contexts I'm going to mention soon? And then we immediately saw that the only way to train a better model is to rewrite everything. There is no other way. And this is why we came up with this idea, and this is why we decided actually to transfer the project to training grounds at this stage. Not because I wanted to see this project implemented in training grounds, of course I did, but also because at this stage it became quite visible that without doing this, you're just going to write more and more and more code for each experiment you're going to make. Okay, so how do we do this? So imagine we have only 2 records in a batch we are processing right now, and we want to build a context for these words. So first step we need to do is to build the context. And the context is something like this. So this is the word ID, a distance or offset in this context between the words and another word ID. So if we just look at if we just look towards to the left, then this table is quite easy to generate, right? So for the word with ID 100, these offsets are going to be computed. I mean, of course, it also matters where the sentence begins, but generally it's not a hard task to compute such table. Then you have the structure that actually looks quite alike to the initial one. You have some index, and then you have a word ID. So this is here is the index, these 2 columns are the index, and this is the word ID. And so you can use extractor to extract all of the morphological and syntax information you need for this word. With the very machinery we already have and we were having for quite a while. And then you will end up with something like this. You know the word ID, the initial word you are building the features for, the offset, and the features. But you still need to get the features for the initial word. And you use some aggregator to do it. So the simplest way is, as usual, averaging and maximizing, minimizing, something like that, right? So this step we have basically covered, and it's available in documentation to training grounds and all the details how to do this. This step this is a simple step, I will cover it a bit later. Now to context builder. So languages are difficult, and if you just look to the neighboring words, you may miss a lot. So consider, for instance, this sentence. He should, with his sophisticated taste and penchant for exotic, like it. So I think in this particular the case, I made an error, a grammatic error in English sentence, because I think this subordinate clause should not go after the modal verb. But unfortunately, in Russian it can. It can go anywhere. At any place in the text, you can see the long dash, and then arbitrary amount of text that is loosely related to anything, to be fair. And yeah, if you look at this word and then try to understand something about this word by looking at the subordinate clause, you're not going to be very successful, because the subordinate clause is completely detached from the rest of the sentence, and yeah, just not usable. Again, if you want to understand where the borders are, it's not that simple. So in German it's simpler, because it starts and ends in particular ways, so you can a little bit parse it in your head, but also not always. In Russian, again, there is no fixed word order. You can place words in any way you like. So yeah, problem. But if you have the parse tree of this sentence, it suddenly works quite well, because on a parse tree it looks like this. So here's the verb of the sentence, should. He and like are related to this word, and also subordinate clause is related to here with the word with. So in this tree, if you look at the context of the word like in this tree in terms of tree-like structures, like brothers, parents, or children, you are going to end up with relevant words. And in order to get not relevant words, you need to go to subordinate clause, but you really need an effort to do it. You can't just jump in accidentally. So what we want to do then, we want to build the context based on parse tree. And providing that the parse tree is correct, which is not always the case, but still we can get the information that is a lot more useful. Again, how do we do this? So the first attempt was, okay, we have this information right from the syntax parser, and we can just implement a very simple algorithms to get brothers, parents, and children of this particular word. And the algorithms are indeed quite simple, but the thing is that all this machinery works batch by batch. So for each batch, you have to run these algorithms, and these algorithms unfortunately have to be written in Python. So it takes ages. So every sentence is easy to compute, but when you try to compute it for hundreds and thousands of words all the time, it just takes ages. So the solution for that is to pre-compute the data frame and then use pandas to perform the required operation. Because really, when we say that something must be done fast in Python, it means it must be done with pandas. So there is no other way, really, right? And we come up with the idea of this data frame that we need to pre-compute. So this is parent, child, and the distance. And that means actually all the pairs of vertices that are connected by the path. So for the verb was, the was is related to whether on a distance 1, and the was verb is related to the on a distance 2. You have to compute this this data frame for all the sentences in your data set. So it will take some time, but it will happen once, and then for each batch you will just use this auxiliary table to do the work. So how do you do the work? Okay, if you want to find all parents, then you just join by this column. If you want to find all children, you join by this column. If you want to find brothers, which is the most relevant feature, to be fair, right? The brothers, then you have to join at this field for distance 1, getting parent, and then all the children of this parent at distance 1. But it is anyway just merges with pandas, so it works fast. And now to aggregators. So what we used was mostly averaging and taking the maximum, not minimum, maximum. Why? Because it looks like it just matters that there is a noun somewhere. There is a modal verb somewhere. It doesn't matter where, it doesn't matter how much, it just matters that there is one. So this is how how the max comes with. Mean, well, also, I mean, we don't really know. We just use what we have in mind, like that makes sense, that might make sense, so we just try. What we really want to do though, at some point, is using the LSTM aggregator. And this is also what I always wanted. Henrik won't let me say something that is not true. I always wanted to try here, because we also have contexts, right? So for each customer, we have the context of his previous purchases. For each article, we have a context of the previous purchases of this article as well. And if we just get the easy access to this information, then we will be able to aggregate on the experience of the customer and use this experience to extract some meaningful features, right? And we expect it to be really insightful. Unfortunately, we are still on this level here. We get the context, we average it, and that's it. But maybe there is more to it. And this structure we have right now with context builder, extractor, and aggregator really allows us to do this. Why? Because there's only one step we need to change, namely the aggregator. Others we have already introduced, we have tested with the unit test and also with our experience. We tried these things and they worked. So now we just need to change a small block in this whole system to get to LSTM models. And for that we just need to transform this data frame into three-dimensional tensor. So word ID goes after one direction, offset goes to the other direction, and the features, so F1, F2, F3, F4, all the features we have, this is another dimension. And then we have it, and then we can get this tensor, feed it right to the LSTM network we can install in our network, and we will get these features for more or less free. And now And now we are, I think, in the best shape to do this as ever before, because we have all this machinery. This machinery was tested and also in NLP as well as in our internal setup. So, small step right now, it's a small step. We just need to write the aggregator, test the aggregator, and then like spend some time trying to understand like how this access should be placed in order to fit to a less tame network. It's not immediately understandable. And we will probably try to do this to our research as well. And generally what we want to do here in the future is this. So first we want to cover more grammar errors, because like we spent some time writing all this code and testing it, and there's little meaning to have all this if it's only for one error. But if you look at it, you see, right? So how does one error different to another? Just on the stage of dataset preparation. So to make an error is easy, right? You look at the grammar book, you pick the rule you want to break, you look for all the right occurrences of this rule in your text, and you change it. That's pretty easy. And then you basically construct more or less the same features, you construct more or less the same network, you just run it, and you can produce one network after another. Moreover, these networks are going to have shared features, because the morphological analyzer and the syntax analyzer, they are not the part of the models. They are not trained. They are the step before the models start to train. So when you use these models, you can just look at text, analyze it with morphological analyzer and syntax analyzer, then apply this network, and you will get your text checked for multiple errors. So this is the idea. I mean, the idea is not to write actually the Grammarly for Russian, because it's more marketing than actual research. The idea is to be capable of writing Grammarly. So not writing it, but being capable to write it. Yeah, and also publish as an open source for just for fun. Also, what we want to do, we want to finish this comparison with Microsoft Word, because we really want to know is 91%. I mean, sometimes it's really hard to tell, like if this error is like, if it's obvious, if it's not obvious. So we want to compare it with a standard de facto to know how to look at this result as something we need to improve or something that is actually perfectly acceptable. Then we want to try to get more features from SlovNet network from under the hood. Again, what we see in anecdotal evidences, when we actually try to analyze the syntax of incorrect forms, we see that when you analyze the incorrect sentence, you get something strange, something weird, something that you shouldn't be seeing. Probably that means that on the underlying level of networks where are still numbers produced, so not the tree structure, but the numbers from which this tree structure arise. So probably these numbers are in some state of imbalance. So it's hard to build the correct tree, and the incorrect tree is built instead. So if we could look at these numbers and detect these imbalances, maybe we will be able to detect errors much faster, just by looking to some intermediate numbers. But we really need to understand how it works inside, how actually this tree is built, but I think that's going to be a splendid adventure under the hood of SlovNet. And my personal wish is to continue with stylistic errors as well, because so this is a highly subjective thing. You may have a Grammarly for grammar, you may not have a Grammarly for style, because the style is different for different authors of different genres. And even in Microsoft Word, the style check is for the official letters. I don't want to write official letters. I want to write fiction, and I would be interested in some stylistic errors that would detect the problems in fiction text and compare it to my favorite authors, so I could write a little bit more like them. So here it's a bit more complicated task because you need to get a negative data set somewhere. Fortunately, we have a huge self-published free library in Russian language, and if you just look at this library, you will see that yeah, it's not very stylish. Most of the texts are not, because those are graphomans. So if you if you compare the grammatic structure of a good text for an author you like and the not so good text from a random source of words, basically, then you might be able to train a network that will gravitate you a little bit towards the style of writing you like. That's it.